So I have been talking about the Hamiltonian simulation problem, and some pieces of the whole scenario I have described. I will have to now put together those things with the major part, the evolution computation, but I will give a summary of what all things have been included in the whole description. So the part which I will discuss today is just the evolution part, which relies on essentially exponentiation of the given Hamiltonian. So the description is some initial state is given. I described last time what are the kind of initial states which are convenient, and then you apply a unitary transformation to it to get the final state, and this ut is what we need to construct, and that is described in this path ordered prescription, because the Hamiltonian terms may be time dependent and not necessarily commute with each other. What we need to assume as this H, so elements of Hamiltonian, which I will just write at Hij, they are efficiently computable given the indices I and j. So the Hamiltonian has a compact description. We assume that if you give the label, you can easily calculate that, and that is not part of the computational complexity analysis. On top of that, we'll assume something more, which is required to do this exponentiation properly, that this H is bounded, because otherwise exponential will go out of control. And on top of that, there is an integral over time. So we have to again assume something which makes the integral easy to do, make it piecewise continuous. So it's like you want to evaluate an integral, you do a trapezoidal rule for each little time step and then put them together in some sense. So that is needed to efficiently evaluate this exponential. Now we went through several tricks to carry out this exponential. So the important part was assumption that we can't do it for any arbitrary Hamiltonian. So we assume that this H can be broken up into a set of independent parts which are easy to deal with. What is the meaning of easy to deal with? This HK are block diagonal, and the purpose of this thing is that they can be easily exponentiated, because exponential of a block diagonal matrix is also a block diagonal matrix. So H is block diagonal, and the U which will come out is also be block diagonal. What is the decomposition? And I illustrated this by some examples. So the D is actually the number which can be called the sparsity of the Hamiltonian, or the number of nearest neighbors, different descriptions. And in the graph theory language is how many colors are needed to make the graph into disjoint pieces. And then once you do this decomposition, the individual parts are block diagonal. And D is some finite number. Okay. Now, what is essentially going to happen is very straightforward in terms of this block structure matrices, and that is because the real part of the linear algebra is multiplication of matrix times a vector. Because that is what essentially this is. Some state is there, some matrix is there, you are going to multiply it. And this is standard stuff of linear algebra. If you have a block diagonal structure, it makes this multiplication easy. Okay. So what is done classically? This block diagonal structure allows parallelization. Different blocks are independent. You can make a parallel algorithm. Each part will work on one particular block, and it will do this multiplication. They are independent parallel streams, and they can be given to a multi-core or multi-processor system. All that is going to happen in the quantum state is this parallelization is going to be replaced by superposition. They are independent streams. If you know how to label them properly with some indices, whatever are sitting over there, you can superpose those components and do it in one execution instead of giving it to different processors to do it independently in case of a classical situation. And there is nothing more than this that can happen. Okay, you don't get anything else out of the quantum algorithm than doing this a simple replacement. Only thing is you have to figure out how to do this thing efficiently. That means you have to find a labeling scheme, which will allow you to put together various components in superposition and then just let it evaluate. Of course, the final vector will be the same size as the initial vector. So we are not just talking about measurement. Measurement is a different story. The all parallel components will come out, all superposed together. How you are going to get answer out of it, that is a different story, and that I'm not dealing with right now. But this is all that happens, and we know how much advantage you can get. So for n-dimensional matrix, n qubits can superpose 2 raised to n equal to n components. And that is what will be the reduction in the complexity. So this advantage, whatever you want to call it, is nothing but one factor of whatever is sitting there. And nothing more complicated than is going to come out. The question is, how do you arrange for this to be possible? So, yeah, this is the overall structure of what is going to happen. There are some more things which I described in the last lecture, and that is related to approximations and errors, because every thing will have some truncation, and I defined in last time certain errors which are part of the discretization. One of them was that the algorithm is a function evaluation problem, and when the individual components have errors, the final thing will be a distribution. And to figure out what is the correct value from that distribution, we have to find out the frequencies of occurrence of each answer, and this basically amounted to repeating the algorithm many times and seeing what is the likely answer. So there was this label which I used, R repetitions of algorithm are needed to get the scaling that this R is going to behave as log of 1 over epsilon, where epsilon is the bound on the error which you desire. So this is one approximation which is part of it. The other thing which I included is a round of error. And that also has a particular scaling that these registers will have some numbers of bits, which I called, I think that's called B, and it's where M is the number of steps in the algorithm, essentially the linear algebra. And there is a log here also. So epsilon is the overall error. There are going to be multiple sources of errors, but because it's a linear algebra, the total error you can say it's bounded by the sum of individual errors, just a triangle inequality. So you can add up all the errors and make all of them of the same size. So yeah, strictly speaking, you should have different epsilon for everything, but I'm just going to label all of them as the same thing. So keep that in mind, that all errors so the errors are all in the values of the vectors. So bound all of them roughly of the same size, so the total thing will be the sum of all the individual errors. I will not bother to distinguish different pieces by giving the epsilon different labels, but it can be done. So this is some part of the description. There is going to be one more error which actually comes from the exponentiation itself. So there will be an error also comes from this fact. And we'll assume that also to be bounded by the same variable epsilon. The exact matrix what is needed and the approximate which you will calculate will not perfectly match, but you will say that the difference is bounded in some particular sense. Which norm you take here doesn't matter too much. It can be linear norm, quadratic norm, etc. They are all of the same size, and that is good enough. So now the job is to describe a procedure to calculate this u tilde efficiently. And since you are doing this multiplication, it's not necessary that u tilde is exactly unitary. If it is approximately unitary, we will be able to fix it in the sense that if the norm of this is 1, this is not exactly unitary, the norm will be little bit different than 1, but we'll say it's 1 plus epsilon, whatever it is, it's still within our bounds. And you calculate with a slightly different norm, the expectation values will be also different by same size of epsilon, and so the measurement results will have a similar bound as a function of some epsilon. So that part doesn't have to be perfect. If you can do a little bit imperfectly, it's tolerable. Okay. So now let me give various things which people have tried, okay, to calculate this u tilde. As I said, the underlying structure is we are going to multiply matrix with a vector. So you are not going to calculate u tilde, but you will only calculate u tilde acting on some state. And that will dictate how many steps you have to take to reach all this exponentiation with a given accuracy. And since I have already introduced this variable m, the first algorithm just is a simple evolution. So take a little bit of time step. Delta t, you have to go total distance t, and this m is the number of steps of the algorithm. You will go a little bit at a time. Okay. And so now the question is to generate this u tilde for that small time step. Again, it's important that this Hamiltonian is bounded. It's not necessary that every problem is a bounded Hamiltonian. For example, one of the common physics interaction, Coulomb potential, is not bounded. So you can't directly plug it in this kind of situation, but if you are dealing with polymatrices and qubits, etc., those whatever you write down, spin Hamiltonians, they are all bounded. So yes, there will be extra work needed if the real physical problem has new properties. You have to define some change of variables or some approximation to get the Hamiltonian into that bounded structure. Okay, that is a different story and requires knowledge of actually the physical system and its dynamics. Okay, I will not go into that part. Assume that some Hamiltonian in some polymetrics basis is given, and then you can do various things with it. So the common procedure, the first one is something which is kind of called the Trotter approximation, and which means that this e raised to I, there's a minus in front, doesn't matter. Okay. I use k. The Hamiltonian in so many different parts. I just exponentiate each part separately. It is an approximation because the different parts inside here don't commute. Okay. So how many parts are there? Well, it depends on the problem defined by this color of the graph or the sparsity or whatever you want to call it. In certain problems, the number can be as small as 2, as we saw in the case of Grover's algorithm. You can just write it down 2 factors, but there can be more than 2, whatever that value of d is. At least 2 are there, otherwise you don't have quantum mechanics. Okay. 2 non-commuting stuff is always needed for any linear algebra in quantum mechanics. Okay. So now the question is, you do this, what is the error? Okay, because I said we are not going to calculate exactly, some approximation is there. One advantage of this description is that in this particular case, as long as your decomposition is also in terms of Hermitian matrices, this is still unitary. Okay, so this is not going to enter, it is unitary, that is fine, but it is not exact. So what is the error? The error depends on all kind of ways in which you can multiply these factors together. There is a whole expansion constructed by Suzuki, so it's called Trotter-Suzuki expansion. The lowest error is order delta t square, but you can rearrange the powers to make it higher powers of delta t as well. The delta t, order delta t part is exact because you can count just by doing a Taylor expansion. One is there on both sides, then order delta t will be just a sum of all the different components, which is exactly included. But the order delta t square is not included correctly because that is where two of the Hamiltonian factors can come in different orders, and that gives a commutator. So that part is something which can be worked out in explicit details, and I want to get the coefficients right. So let me look up the formula which can be worked out without too much trouble. So the error, or rather I can write, so as I said that both these factors are unitary, so whatever the error is, it is still described by some unitary operator, but it is of the order of delta t square, and you can evaluate this E2 explicitly, and it has a form I by 2 sum over I less than j hi hj. These are the two pieces of the Hamiltonians which don't commute, and of course this is not restricted to only delta t square. There will be higher order terms, delta t cube, delta t4, etc. So that stuff is left over there. But this is explicit quantification of the error. Two pieces will not commute, and they will give some correction, which will be the result. Now there are tricks to make this approximation start at a higher and higher order. Okay. And going to arbitrary order actually doesn't help very much, but knowing one of the next steps is actually convenient, and that is the third order of this expansion. So I can also write this thing in a little bit of a clever fashion, which is some reasonable exercise which one can carry out. I have to put half. That I symmetrize this whole product of the structure. One of them goes from D decreasing down to 1. The other one goes from 1 increasing up to D. And the symmetry then guarantees that the correction, whatever it is, starts at the next order. Okay. This is a kind of well-known trick in linear algebra. If you have never seen it, it is worthwhile proving it. But just symmetrizing this various factors together gives you a higher accuracy. Okay. And this E3 can be calculated. It's a little more complicated, but I will write down the formula. Incidentally, this detailed algebraic formula can be found in many places. It is there in one of my papers as well, for which I have given the citation in the lecture notes which I have been putting on the web page. Well, not the full lecture notes, but at least the description of all the topics. So they are all papers available on archive, and you can look them up, or well, if you want to verify them yourself, that is also fine. So this has different kind of terms. Let me just write it down for the completeness. But they will involve triple commutators. Well, triple means there will be 3 factors of Hamiltonian. So it's one commutator and then the commutator with another term as well. This is I, comma, Hj, Hk. Doesn't give you a great deal of insight, just to illustrate that it can be done. Okay, so there are expressions of this type. The main point is that it will reduce the correction to one higher power in delta t. So now one can estimate the total error by counting this m number of steps and how do these various inaccuracies build up. It's all going to be simple linear algebra and this identities of various inequalities. Mostly it will be triangle inequality or the Cauchy-Schwarz inequality, nothing more than that, because all you are doing is matrix times vector multiplication. But that is what needs to be estimated to get the idea of the total complexity. So this truncation, so error, I will just it will be of some particular form. M is a number of steps. There will be some steps. One of them can be the exact one, the other one is approximate one, and you need to calculate the difference between the two in some sense or the other. And this is rather trivially bounded because I can write this as a product of two terms, one of them x minus y, which is always a factor of this kind of a difference. Other thing is all the part of the sum. Okay. And this is rather trivially constrained because all the terms over here, x and y, they are coming from unitary matrices. So they can be bounded by 1. You take the worst case, which is all of them are together, all of the identity that produces a factor of m, and then you have the error in individual step. So it's a rather simple bound, but it tells you how the inaccuracies in individual steps add up. And what our job is to now calculate this m to some precision, because then we'll know the total number of steps in the algorithm, how much work you are going to do. So here in this particular case, this difference is exponential of the part which we want. So x and y are basically these terms. I'm just writing it down more explicitly. This is a general result. What we need is this particular application where the difference is this error part and the other part is identity. What is the result for this? And that can be, well, I'm not going to do a very hard job, just do the first order Taylor expansion and assume that it is going to be good enough. And I plug in this definition of delta t, whatever is here. So it's m times 1 minus k delta t is now replaced by the total evaluation time and then this norm. This is essentially the overall scaling formula. The error is defined by the magnitude of the commutator. Now, how big this commutator is, it will depend on the problem. Individual terms, we assume that they are bounded. You can say that they are all scaled to order 1. That can be done because you can rescale h by rescaling time. So if h is 1, the time will be correspondingly adjusted to some value. That is not a problem, and the time is going to appear over here. But even if you say that the individual parts of h are of order 1, you don't know what is the scaling of this commutator is. And you can say the worst case, if these objects are of the order 1, the commutator will also be of the order of 1, but it can be smaller. And how big or large it is problem dependent. You can't make an ad hoc statements, but if h is say order 1, then commutators are bounded. You cannot exceed some power, whatever it is. Okay. So now we can put together the scaling or the counting of how much work you need. So, okay. Now you have to count all the terms, whatever we have talked about. So one of them is this number of steps which you have to take. Then the other stuff was the number of repetitions. I have to run the algorithm many times to get the error. And the third part I will just call a single step work. So this is matrix vector multiplication. Because all you are going to do is, with all the jugglery, you are going to take one of these and act on that particular vector, and you went through all the analysis of how you are going to do that in linear algebra. Whatever it is, it will be block diagonalized and multiplied in some particular manner, but that will require some number of operations, and that is the place where this dependence on the size of the matrix and how many components you superpose goes in. What here made explicitly is only the time part of it, not the space part, which is the size of this matrix, which is buried inside here. And now let us put all these things together. I'm not going to touch that R and C, which are independent factors. Just put M properly, and that comes from solving this equation that this stuff is has to be bounded by, again, the generic stuff, some epsilon. because this is the total error after m steps, and that I called epsilon, and we have produced an expression for it. So this is needed. And that allows you to convert this value of m as a function of epsilon. Okay. This thing is fixed, some evaluation time we are given, and this depends on the problem of the Hamiltonian, but it has some norm. And so while you invert everything, you have to take the negative power or fractional power to get this linear order. So the dependence goes like t to the power k divided by that 1 over k minus 1 is coming from the power of the epsilon, and then there is r and c, which I'm not going to touch for the time being, but there is a epsilon power which has to be put together and which goes like 1 over k minus 1 times r by 2. This whole thing is in the denominator. Something got embedded inside here, and that is this repetition scaling of the algorithm, where I said we'll repeat the algorithm r times and choose the result by majority rule. Okay. So that had a power of r by 2 extra coming in together with epsilon, and I have included that correction over here, because the final error is not this epsilon, but you repeat the algorithm multiple times and suppress it down to some r by 2 power. So this becomes the final result, and that is what is necessitated by this Trotter expansion. And it shows the limitation about how far you can go. It has two features which we don't really want. One is a power of t is greater than 1. As I said, if you had a perfect quantum simulator, you just run it linearly in time and you don't have to do all the algorithm. The algorithm is worse. If you take, say, the second order, whatever it is here, it will actually become t square, which is much worse than the linear one. Even if you do this, then it will be 3/2. So unless you go to very high order, but that means the extra work will become equally large, you don't get good scaling in time. And The dependence on epsilon is actually worse. Only power law dependence on epsilon. Remember, what we are trying very hard to argue is we should get an algorithm which goes as log over 1 over epsilon, and this one doesn't do that. Okay, so that is a much bigger problem, because that means the convergence of the algorithm to the desired answer is going to be much slower. And so, yes, this is a well-known topic in lots of papers which you look up on this Hamiltonian simulation, but as soon as you use Trotter formula, you'll end up in this kind of trouble. And that is not good enough. So the question then is, can you find an alternative? And even today, there are lots of algorithms which they take to some stage and they say we'll use Trotter formula after that. That is not going to give you a good scaling as far as complexity is concerned. This other stuff was also there, which produced some scaling. So that is actually part of this C. So how many bits will be needed? This matrix vector multiplication. So this C scales as various things which I had introduced. One is a sparsity. The other was a matrix size, and the third is the number of bits. And as I explained last time, any function can be approximated by the polynomial, and the evaluation of polynomial goes as a cube of the number of bits. So this is where the depend on the size comes in. Okay. So there is a space dependence, which is where you can get an advantage using superposition, and what this evaluated is time dependence. How many steps you need. Both are part of the complexity analysis, but they kind of separate out that, yeah, this how many steps, and each step you can calculate with some effort. Okay. So now comes the question about what you should do to get out of this Trotter type of approximation. And the solution is kind of result which is generic, and I want to emphasize it once again, that when dealing with a quantum algorithm, don't try to do calculus. Taking this small step and doing integration is not the optimal way of doing any exercise in quantum logic, you actually need to take situations where the steps are not infinitesimal. You don't calculate the gradient, you calculate the whole integral in one step. And this will require a totally different philosophy. Delta t is not small, it's going to be order 1. And we have used this scenario in discussing various implementations of quantum circuits, and I will write them down. So when you want to rotate a qubit, you do not calculate the gradient and apply infinitesimally delta t, delta t, delta t. What you do is use the Euler angle decomposition, which goes from any initial state to any finite state in a finite number of steps, irrespective of the distance. So we also used it in Grover's algorithm. We did not implement the rotation in finite step, we use reflection operators. The reflection operators by construction are order 1. So they don't have any finite part, its eigenvalues are plus and minus 1. So this is a generic feature. So if you want to get a good quantum algorithm, try to figure out where you can take steps which are order 1. Otherwise, the scaling is going to be not what you call efficient. So how do you do that? Well, if this is not infinitesimal, then there will be error. I did some expansion over here in the powers of delta t. But let us take that expansion literally and just ask what will it require. So I can do these steps, whatever h you have to use a different index, all doesn't matter. Is just the standard truncation of the Taylor series. What it does is, yes, you need to keep track of higher order terms because this delta t is not small. But what helps is this factorial sitting in the denominator. How many terms you need to keep? Well, this is going to grow faster than exponential as well. So as soon as delta t is bounded, I'll put order 1. Is 1 over n factorial will tell that if I take 5 terms in this series, it will be a good approximation. Because the factorial is going to suppress all the higher order terms. Remember that h I have already said it is bounded. Delta t is not small, but it is still bounded. And so you take this to sufficiently high order, you will have a good approximation. And instead of using all this complicated stuff, I will just use that. Okay. All I have to do is the same thing. This is a matrix. This is also a matrix. And ultimately, I am going to do matrix times vector multiplication. And since this H is broken down into block diagonal part, all that multiplication will go through. What is the price you are going to pay? Is that you will evaluate these powers up to some value p. So when you do this matrix times vector multiplication, you have to do it p times. Just one, whatever is counted over here is not enough. Okay. So what I was counting over here, this complexity, I have an additional factor of p. Because C was just a single vector matrix multiplication, I have to put an extra factor of p and then see how things will behave, but I will no longer have to worry about this delta t and m separately, because this is finite, which is order 1. That means m is equal to t. That was what was written over here. So that part simplifies. And then I have to now ask the balance of the counting, whatever happens. And here, the result is that the scaling basically changes rather drastically. And that has to do with the truncation of the expansion, or well, there is one more thing which is actually useful to know, and that is a well-known result from numerical analysis, that there is a better expansion than just a Taylor series. And that is something which is called a Chebyshev I will come back to the question of finding a good value of p and the scaling little later. Let me give a reason for this, and why the Chebyshev expansion does better. The answer is rather straightforward, that Taylor expansion is constructed about one particular expansion point, typically the end point of the interval. So this error of truncation will be small at one end and large at another end, depending on how big this step is. What Chebyshev expansion does is the error is sort of uniformly spread out over the whole interval from 0 to delta t. and it's a well-known trick in numerical analysis, and so the series converges faster. That is a interesting result, and the function exponential is kind of simple enough, so I can write down analytical formula, which you can look up in mathematics books, that this can be written just like this exponential series in terms of some coefficients. So no, it's not h. So this is Chebyshev polynomial with the important property that it is its value is in bounded. I should between -1 and 1 for x in the same interval. Explicitly, it is defined Tn of x is cosine of n times cos inverse x. It's all recursion relations are very easily listed. You can find them in a textbook, but that is for the purpose of writing code. Important property to remember that it's a bounded polynomial, and since h, I am scaled it so that it's a norm is of the order 1. I can scale it so that this thing is also of order 1, or whatever operator is going to come out, it's bounded with norm 1. What this expansion did, just like is over here, it separated the dependence on time and the variable. Same thing happened here. Time is only here, the variable is over there. So now the question is, what are these coefficients? And yeah, type 1, the first one. It's cosine. The other one is sine, and that we don't need. Okay. So both these coefficients are kind of known. They are the Bessel functions. Here there were just some powers, more complicated stuff like J0 to Jn or whatever is going to appear. Important point is that these are again bounded functions. Bessel functions oscillate, but they don't blow up. And that oscillation part is very crucial because that is what keeps this expansion much better behaved than that. And if you want to count the power, then there is a scaling formula. So J and T large T behaves like T to the power n, but the denominator is the one which is more important. Instead of just n factorial, which was over there, there is an extra power of 2 to the power n. And that means the series, whatever it is, if this is bounded, it will converge faster because of this extra 2 to the power n. You can say how much it will save. It may be just saying a factor of 2, but that is still useful. So this is what I mean by saying that how much better it does. You will have to find a value of p, and here the value of p will be correspondingly smaller, whatever it is. The series converges faster. Okay. So now we can go to the step. What is a good order to evaluate this expansion? And that basically means that when I truncate the series, I will throw out the higher order terms, but they are falling off with some order, and I will put a bound on it. And that gives us scaling result, which can be evaluated, and I can basically evaluate the truncation bound. And the error is well, if I cut it off at some particular point, it's less than some of all the coefficients. Okay. That is because this polynomial is bounded. I doesn't do much. I just have to find out how many terms of this expansion are neglected, and the triangle inequality says that I just have to sum up all these terms. Or actually, it's better to do this. Okay. And that expression I have for large order, this is what is there, and the various factors are not too complicated, so you can sum it up. Okay, so this is or not exactly sum it up, at least you get a good bound. And actually, yeah, here I'm writing here, but this is what I need is actually delta t. Because I'm going to apply this expansion for every step which I take, which is delta t. Delta is order 1, but whatever it is, that is the part I need to count. And that series is a geometric series in some sense, so it can be bounded. by just taking the leading term. This is again a bound. So I factored out the leading part, the first term inside this, and the other terms are now falling off with some power of it and also together with the factorial. And I can ignore some of them to be able to sum up the terms in a nice fashion, and that is done by just counting this extra power and giving a bound that this is the sum of the geometric series. At every step, powers of this and this increases by 1, so this delta t and 2 are as it is, but the powers of this are becoming higher and higher. So you will get p plus 2, p plus 3, p plus 4, etc. But whatever it is, they are all, first one is p plus 2 and all the other ones are larger, so I will just put a bound on it. Whatever it is, p plus 3 is always bigger than p plus 2. If I do that approximation, the geometric series can be summed to produce this, and that is a good enough result that I will make sure that this extra factor, whatever it is under control. And all the scaling of the algorithm will be then governed by the first factor, which will determine what is the power of p. And that requires inverting that function. So so now you have this relation still is there. What we need is the total error. There was a factor of 2 somewhere. So there was a 2 here, so it's actually half the error. So it doesn't matter, it's something that can be taken care of without too much trouble. But the condition becomes this, that 2m, these things, delta t, p plus 1, 2 raised to p plus 1 times p plus 1 factorial times 1 minus delta t times 2 times p plus 2 inverse and all that accumulated error is less than epsilon, whatever criterion I impose. Okay. Remember, all this stuff is what I just calculated is sum over all the Bessel function. And now this is in a form where I can determine p. All the other stuff is known. And you can do it iteratively or in a iteratively probably easy. I am going to put this number delta t of the order of 1. Okay, so I should correct this. This is not order 1. It is theta 1. Theta is actually exact size. So if I do that, then this stuff goes away. M will just become equal to t, the total time. and there is epsilon. This stuff also can be safely ignored in a with sufficiently high order, which will come out when you solve for p. And I have to essentially solve for this power involving p and the epsilon. All the other stuffs are becoming constant, and I will write down the answer. It's a scaling relation, but that is good enough. So it is log t by epsilon times log. Okay, this is order again. The good approximation for this factorial is roughly the leading term is p factorial goes as p to the power p. So that is where it comes from, but the first part is easy to guess. Where did the t over epsilon came? Because delta t I put equal to 1, then m become equal to t, and that t over epsilon is the whole thing coming over here, and the other side is this 2 to the power p, which produces this log t over epsilon. That is where the whole result is coming from. And of course, you include the scaling of the factorial, which is more than the power, then there is the subleading term, which is log of log, but that is a small correction. Every time to take a log, the whole value basically drops. The important point is you got the epsilon inside the log, okay, which was not the case here. Okay. So I can now write down the final answer, which is the overall scaling of the algorithm, and that will give the contrast with the Trotter series. Yeah. This one. Yeah, so I took this formula and inverted it, okay, with the result delta t 1. M then is equal to the time. Okay, so then this becomes t divided by epsilon. I change the side, that is where this factor is coming from. This whole thing I can take to the other side of the equation, but p is in the exponent. So p then becomes log of whatever was over there, which is log of t over epsilon. Now, if you write the log on both sides, means p factorial goes like p to the power p, the leading term. So if you take log, then you will get a factor of p, just like what will come from log of this, but in addition to get another log p as well. And if you re-express the first iteration will just give p as this, then the second iteration you include the log p, then it will produce that. So this is, and so what is the complexity part which I can compare with this? there were m steps, but now there was an extra factor of p, and there was r and c, whatever they were over here. They don't touch. I changed the m because for every iteration I have to expand this series up to some pth order. So this is the extra stuff which came in. But now we can put in this time dependence explicitly. M is nothing but t, capital T, which I was using. P has only logs. And the repetitions and the effort required to do this multiplication, which is, I wrote down whatever is here. That is unchanged. We are just going to still do the multiplication, but the dependence on epsilon changed drastically. And the time dependence is almost linear, little bit of logs inside. So this is much better than this Trotter scaling algorithm. Of course, people ask whether you can really make this linear in time. Nobody has succeeded. This is as far as what has been done, but people are happy. These logs are generally something that can be tolerated in some sense. The main feature is that this epsilon went inside the log. So it converges to whatever the result in a much better fashion. So this is essentially the story of the evolution part, how to do accurately. Yes, you have to play with some tricks and calculate the bounds, but the methods used are very simple. Most of the time it is something like this. It's a triangle inequality. You are not doing anything more complicated than that. And you sum up series, the geometric series can be summed. You can simplify the bounds to convert everything to geometric series, and you get a desirable result. Of course, in a practical situation, now you have to ask which are the Hamiltonians which will have these nice properties. I have assumed all kind of things over there, that they are a bounded Hamiltonian with this sparse interactions of the graphs, etc., and that got buried inside some structure like this. But this is where the scaling with respect to the size of the system will go. This gave the time dependence and the approximation accuracy, but how fast the system size will grow is essentially buried inside here. You have to do a good superposition of these block diagonal matrices.
So how do we accommodate the R threads?
It will go, but it will come with this epsilon getting some power, but since epsilon is already inside the log, it doesn't matter too much. I mean, you can get an overall factor, but that is okay. So now, just one last comment, that everything here depended on the decomposition, that I could make a good block diagonal decomposition, and that was possible only when this matrix was sparse. Okay. Are there any other situations, other kind of matrices where the sparsity is not there, but it's the same kind of tricks can be employed? The answer is yes. So I will just write down some names. Okay. So the sparse matrices, the property is they have order d times n non-zero elements. They will be quite general. But have we seen the matrices which are not sparse, but somehow the non-zero or the not non-zero there, distinct elements are still of the order of n. If the general matrix, there will be n square different elements, and that you can't handle because of the superposition trick will reduce one n to small n. You can't do anything more than that. But you can ask whether order n non-zero elements. I can't say non-zero anymore because that is already taken care of. Distinct. And it turns out that there are special matrices which may have n square non-zero element, but only order n of them are distinct. And we have seen one of them, which is discrete Fourier transform. It's cyclic, e raised to I some k divided by n, k goes from 1 to n and then kind of repeats. So there are n square non-zero elements, but only n of them are distinct. And the way it worked, when we simplified it while dealing with quantum Fourier transform, which could break down the same scaling. And the way it occurred, so the DFT matrix, it factorized. So you could do a transformation on individual qubits and then build it up to do some 2 raised to n. Completely the matrix factorized. That is not superposition, but it's still a very useful approximation because, not approximation, it's a very useful trick because the factorization is classical. And the standard for fast Fourier transforms also use it. They can't do superposition, but they certainly can do factorization, and that is where the calculation simplifies. You get an advantage breaking down from this to this. And it's a matrix which is not sparse, but which allows a simplification. So that's where we landed up using that construction in Shor's algorithm for period finding. Okay. For a matrix which was not sparse. And there are other matrices which you can find in the mathematical literature. Some things like this can be examples for that, but you have to design an algorithm for that in more detail. Maybe somebody has done it, I don't know, but some other trick will follow. One of them is called a Toeplitz matrix. The Toeplitz matrix is a structure which has all the elements on the diagonals and the off diagonal lines parallel to it, they are constant. So it has one value for all the elements here, another for all the element here, the other third one, all that over here. So that is one example where some other linear algebraic trick may simplify the simulation by some generalization of this quantum strategy. I don't know the answer, but that is something which may be possible. This one is known, the discrete Fourier transform, we have used it all the time. So then there are something called a circulant matrices. They are actually in some sense related to the Fourier transform. You go along a row and it goes around cycle, and the cycle is basically shifted from one row to the next, etc., similar to an acyclic group. So these are cyclic. Then there is another matrix which appears in linear algebra, which is called Vandermonde matrix, which is essentially powers along each row, starting with some 1, x square, x cube, etc., up to some order. There is yet another version called a Hankel matrix, where the elements are constant, not along this, but the other diagonal. It has a structure of that type. So these matrices appear in certain applications, not necessarily Hamiltonian simulation, but some other situations may find use for it. And in particular, I know that these other kind of matrices are common in signal processing. And Fourier transform is something which is common in signal processing, routinely used. And these matrices also appear in various kinds of signal processing. Whether some quantum algorithm can be made to apply in those situations, I think it is an interesting problem, but something should be possible. Main point is that you can't have n square elements, you need only order n. Then you can play various tricks with them. So, okay, I will stop here.